If you apply E equal to E naught sine omega t in an LCR circuit, as a result you are getting a current I equal to I naught sine of omega t plus or minus phi, where phi is defined as tan inverse of XL minus XC by R, whereas the maximum current in the LCR circuit I naught is actually equal to E naught by Z and E naught by square root of R square plus XL minus XC the whole square. From this the maximum value of this I naught current is when the resistance is the minimum possible. So that I naught's maximum value possible comes when E naught by the impedance minimum. We discussed that impedance minimum value happens when XL is equal to XC. When XL is equal to XC, this term becomes 0. It is root over R square becomes R. So the minimum impedance in an LCR circuit is R. Suppose if you draw this curve, say you have, just take current in the y-axis and angular frequency in the x-axis, omega in the x-axis, current in the y-axis. See, when XL is equal to XC, we know that L omega naught equal to 1 by C omega naught. So omega naught is equal to 1 by root over LC. When the frequency is omega naught, the current is the maximum, and that maximum value we know it is E naught by R. On either side, whether the frequency of the circuit increases according to, because we know XL is L omega and XC is C omega, so when the omega value changes, then the current decreases on either side. And if omega value increases also, the current decreases on the other side. So the current is the maximum when omega naught. So at what angular frequency the current is 70% of the peak current. Suppose at this point on either side, let's say if this E naught by R is the maximum current I naught, so this value of current, let us say 1 by root 2 times E naught by R. So the corresponding angular frequencies on this side are, let us say, omega 1 and omega 2, and this is, let us say, delta omega, means this will also be equal to delta omega. So this total frequency difference is called bandwidth. 2 times delta omega is the bandwidth. So the narrower is the bandwidth, the higher is the sharpness of resistance or the quality factor of the circuit. What if the circuit is a high quality one? Then the response curve will be very narrow. This is exactly omega naught, and 70% of the current will come. So the narrower the bandwidth, 2 times delta omega, higher the quality of the circuit. Or if something like, if the circuit is not of good quality, then the bandwidth will be like this. So 70% of the current will be here. So this is the peak current, this is 70% of the current. So this is going to be 2 times delta omega. So quality factor or Q factor is inversely proportional to the bandwidth. 2 times delta omega is the bandwidth. Or it is defined as, the quality factor is defined as the original angular, the resonance frequency to bandwidth. The quality factor is defined as the resonance frequency to bandwidth. Resonance frequency is omega naught, the bandwidth is 2 times delta omega. Here omega 2 is actually omega naught plus delta omega, whereas omega 1 is omega naught minus delta omega, and omega 2 equal to omega naught plus delta omega. So let us try to find the quality factor of the circuit. So we know that the quality factor we are going to find out, it is when the current is 1 by root 2 times the maximum current. So what is the maximum current? Maximum current is E0 by R. What is 1 by root 2 times the maximum current? So 1 by root 2 times I0 maximum equal to E0 by root 2 R. So that means, see, at the resonance it is E0 by R. So other than, say, at omega 2 and omega 1, it is not at resonance frequency, some other frequency. So the impedance will not be minimum, it will be taking this form. That means E0 by Z must be equal to E0 by root 2 times R. So E0 by Z is equal to root of R square plus XL minus XC the whole square must be equal to E0 times root 2 times R, which means that these two must be equal. So square root of R square plus XL minus XC the whole square must be equal to root 2 times R. When you take square, so it is R square plus XL minus XC the whole square equal to 2R square. When you subtract this and take square root, so XL minus XC the whole square equal to 2R square minus R square is R square. When you take square root, the next step is XL minus XC equal to R. And we know that XL is L omega 1. Let us take either omega 2 part or omega 1 part. Let me take omega 2 part. L into omega 2 minus 1 by C omega 2, because we are considering the case when current is 1 by root 2 times the peak current. So the 1 by root 2 times the peak current here will come either at omega 2 or omega 1. So we are writing that XL and XC for either omega 2 or omega 1. Either way you will be getting the same answer. So R. So what is omega 2? Omega naught plus delta omega. So here L into omega 2 is omega naught plus delta omega minus 1 by C into omega 2 is omega naught plus delta omega, which is equal to R. So the next step I am taking omega naught out. L into omega naught equal to 1 plus delta omega by omega naught minus 1 by C omega naught equal to 1 plus delta omega by omega naught. But at omega naught XL is equal to XC. So L omega at resonance frequency, L omega naught is equal to 1 by C omega naught. So I can write 1 by C omega naught as L omega naught. So the next step, L omega naught into 1 plus delta omega by omega naught minus 1 by C omega naught. I am writing it as L omega naught. So it will be coming, this thing I am taking to numerator. So 1 plus delta omega by omega naught whole power minus 1 equal to R. So delta omega is very narrow for a quality circuit. So delta omega is a small value, by omega naught becomes a very small value. So I am taking L omega naught out on both sides, I mean from both the terms. So 1 plus delta omega by omega naught minus of 1 plus x whole power n is 1 plus nx. Here it is whole power minus 1, so 1 minus nx, and that is equal to R. So when you multiply inside, you are getting L omega naught into 1 plus delta omega by omega naught minus 1 plus delta omega by omega naught equal to R. Actually, if we had started out with L omega 1 1 by C omega 1, here we would have got minus 2 times delta omega naught, but that is still fine. We are only concerned about the number. So L omega naught into 2 times delta omega by omega naught. So this is the reciprocal of the quality factor or sharpness of resonance is equal to R. When you take reciprocal, I mean before that, 2 delta omega by omega naught equal to R by L omega naught. L omega naught is actually XL. At that condition, L omega naught is actually equal to 1 by C omega naught. So 1 by C omega naught is Xc. In this when instead of omega it is omega naught, means resonance condition. At resonance condition XL is equal to Xc. So this is R by, you can write it as XL or Xc. So but quality factor or sharpness of resonance, quality factor or sharpness of resonance, sharpness of resonance equal to omega naught by 2 times delta omega. That has come out to be XL by R. XL can also be written as Xc by R. So the sharpness of resonance or Q factor can be defined as omega naught by 2 times delta omega, which is XL or Xc by R. But XL is L omega naught by R. But resonance condition, when XL is equal to Xc, when L omega naught is equal to 1 by C omega naught, we know that omega naught is 1 by root over LC. That you substitute it here, L into 1 by root over LC by R. That is equal to 1 by R into root over L by C. So there are very many terms for quality factor. So Q factor is defined as the ratio of resonance frequency to bandwidth. So it is called what? Resonance frequency to bandwidth. And resonance frequency to bandwidth happens to be XL by R. It can also be Xc by R. XL means L omega naught by R, or 1 by C omega naught R. In other words, it is 1 by R into root over L by C. These are the forms of the quality factor or the resonance frequency.